So, ja, guten Morgen zusammen. Ich hoffe, Sie haben die Osterpause überstanden. Hausaufgaben gingen oder war das viel zu viel Arbeit? Wer fand das viel zu viel Arbeit, den letzten Übungszettel? Gut, ja. Sie hatten ja 2 Wochen Zeit, ne? Ich hätte dem Markus gesagt, mach's extra schwer. Ich mache mal ein bisschen den Ton leiser hier. Ja, ich hatte den Dr. Dürmuth gebeten, das extra viel Arbeit zu machen. Ne? Dafür hatten sie auch keine Vorlesung. So, ich mache gerade mal in Deutsch eine Sekunde Einführung. Was wir heute machen, ist wahrscheinlich so mathematisch der anspruchsvollste Kram, den wir machen. Ja, ist doof, dass es um 8:30 Uhr ist, weiß ich. Ne? Seien Sie dabei. Ich werde Sie ab und zu warnen, jetzt aufwachen und so weiter, aber probieren Sie dabei zu bleiben. Ich weiß, das sage ich öfters, aber das ist definitiv heute die 90 Minuten. Das sind keine 90 Minuten, die wollen Sie sich hier aus dem Buch reinziehen, okay? Können Sie machen, aber kann ich sagen, ist der Sonntag weg, ne? Wenn Sie hier wach bleiben und arbeiten das danach 3-4 Stunden, hat sich die Sache erledigt. Wenn Sie den Kram alleine machen, würde ich sagen 10 bis 15 Stunden. Also ist der Deal, entweder jetzt wach sein hier, ne? Auch die Reihe da oben, hallo, ja, Sie auch, ich erzähle ja gerade was Wichtiges. Jetzt wach sein, die 90 Minuten, würde ich sagen, haben Sie 4-5 Stunden gespart für die nächste Woche. Guter Deal? Ja, ne? Okay. Okay, so, what we've done over the last few weeks. I think we spent 3 weeks or so on dealing with various instances of the discrete logarithm problem. So what we did in particular, we introduced the DL problem in ZP star, that was the first week, and then we did 2 crypto systems that are based on the discrete log problem. That was the Diffie-Hellman key exchange. And we did, last time we met, we did encryption using the Elgamal scheme. So, and I think there are 2 reasons why this whole DL problem is really cool. First of all, and it's kind of, you can view that as a 2-axis, 2-dimension thing. First of all, using this DL problem as a basis, you can develop different crypto systems. And what we've done so far, we did the key exchange, we did encryption. There's one third big thing you can do with public key and cryptography. Does anyone know? I think I've wrote that down at some point. I'll tell you, digital signatures. Okay? There's 3 big things you can do with public key cryptography. You can do key exchange, you can encrypt stuff, it's actually the least interesting one, and you can do digital signatures. Digital signatures, we are actually starting in 2 weeks, we start with digital signatures. So we can all do that with discrete logarithms. So this is the one dimension, okay? The other dimension, this is maybe even cooler, and this is what we're doing today. We don't have to do discrete logarithm problems in ZP, so we can build completely different type of mathematics to build similar protocols here. Okay, that's what we're going to do. Okay, so far we took DL as a basis, DL problem, and we developed security services. This is what you call a security service, key exchange, encryption, digital signatures. And we're going to talk more about security services. And now we're going in the y-axis, if you wish, right? We do the other thing you can do. This is key exchange, encryption, signature, blah, blah, blah. And now, what we've done so far, we looked at the discrete logarithm problem in ZP, and now we look at the other thing, namely elliptic curve. Okay. This is kind of the world of discrete logarithm problems. And today we only in quotation marks, we only have 2 topics, namely we're going to talk about introduction to EC. EC stands for elliptic curves. And then a major part is actually developing the group operation, whatever group operation is. Okay. By the way, what is the group operation if we talk about discrete logarithm problem in ZP here? What is the group operation here? I refuse to continue today before I get an answer. So what kind of group do we have here? Multiplicative group. Yeah. So what we're doing here is a group operation in A times P mod P. This is very simple. That's a group operation. What the goal is of today, by the end of the 90 minutes, what we want to have is something which is also a group, a cyclic group, blah, 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 blah. But it will look very, very different. Very different type of arithmetic we're doing here. Okay? So, buckle up, schnallen sich an, get ready. So, as always, we start easy with introduction to elliptic curves So first of all, is the question, why are we doing that? I mean, it was kind of a nice thing that I, draw this funny diagram with this 2-dimension, but the big question is, why is it even necessary, right? We have discrete logarithm in ZP, we have Diffie-Hellman, we can do digital signatures, as you will see, we can do El-Gamal encryption. The big motivation here is, which I should show you a page from our book here. Schön doof. Okay. That's a good sound. Yeah. Yeah, we're getting close. Okay. So this is a very interesting table in our textbook. Okay, is that readable? Yeah. Was? 156, 156. So, in case it's not readable, it's not that important. It's just to motivate you. Okay, if you still have a sleep, that's perfectly fine. I'll wake you up in a little while. So, what this table deals with is we have these three types of public key crypto system, and what we've done so far is this row here is RSA, and here different security levels. So this compares to an 80-bit block cipher, 128-bit block cipher, 192 and 256-bit block cipher. Here are the bit lengths you need for RSA to get the same level of security. For instance, IAS, kind of the standard AES that people use in practice is 128-bit. In order to get the same level of security, you have to use RSA with 3,000 bits. Good luck. Good luck meaning this is really slow. It's a pain to do arithmetic with 3,000 bit numbers. We don't have only RSA, we can also use our discrete logarithm, and I just called this here discrete logarithm. What I mean is discrete logarithm in ZP. Again, if you want to have the same security as RSA with 128 bits, again, you need 3,000 bits numbers. This is really slow. We don't like to do that. Okay? So this is motivation. What we're trying to do today is, can we find a public key crypto system that doesn't need these absurdly large numbers? And we're not that really worried about the length per se, but the computations that are involved. I mean, just multiplying two numbers with 3,000 bits is really bad. I just talked with Stefan, one of my PhD students, 45 minutes ago. He is doing on a small 8-bit microprocessor that you find on smart cards. He's trying to do 600-bit arithmetic, and his crypto system, it's code-based cryptography, blah, 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 a really weird thing. He just needs essentially one multiplication. This is for this protocol with 600-bit numbers. It turns out this is already, about 10,000 operations for doing one multiplication with the 600-bit numbers. This is 600 bits. Here we have 3,000 bits. Okay, so this is really slow. And what you see here now, the third line, this is really, really interesting. With elliptic curves, you need much shorter bit lengths. In order to get 128-bit security, you get away with 256 bits. Okay, this is, not in one sentence, but in one table. This is the big motivation, the big promise, das große Versprechen that elliptic curves hold for us. It's computationally much more efficient. It's much smaller. And all the sexy applications that people like us like, modern smartphones, the BlackBerry, the satellite radio in the US and stuff, all of the sexy applications, these embedded applications, most of them, they don't have RSA built in, they have elliptic curves. So this is, if you wish, this is the crypto system of for sexy new application. All this mobile stuff, they normally, you have to be careful, but very, very often they use elliptic curves as opposed to RSA. So that's the kind of crypto system of the future. Okay, so the motivation here is find public key family. Why family? It's again, it's not only one crypto system. It's not only key exchange. It's key exchange, it's encryption, it's digital signatures. You can do everything with elliptic curves. Find public key family with shorter operands. Okay, so if you compare table, it's table 6.1 in our book. I don't know where this is. Yeah. Okay. So the idea that we're following, because we saw, hopefully you were awake the last few weeks, we saw that we can use discrete logarithm problems for building crypto system. So the idea at this point is, can we find another cyclic group and it's actually pretty easy to find cyclic groups. There was one homework assignment 2 weeks ago, I don't know if you recall, where we gave you a cyclic group where the DL problem was really easy. Do you recall that? Where we did modulo P and addition, right? So that's a cyclic group. You have all these nice group properties. It's really bad. You can't use it for a crypto system. And why was that? Because the DLP problem wasn't hard. We want to have a cyclic group where solving the discrete logarithm problem is very, 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 very hard. So can we find another cyclic group in which the DLP is difficult Fragezeichen, question mark. Ideally, more difficult than in ZP or ZP. And I can already give you the answer. The answer, if you really followed what we've been doing here the last 2 weeks, is yes. Because the reason that, again, we go to this middle line here, discrete logarithm in ZP. The reason why do we choose 3,000 bit? Why do we have to choose this really, really long numbers in order to get this 128-bit level of security? It is because there are fairly powerful attacks available, which we haven't really discussed. I gave you a little bit an overview of this index calculus method. So there are fairly powerful attacks available, which force us, we are the good guys, we're the people who build Blackberries, for instance, right? That force us as the good guys to go up to 3,000 bits because there are ways of solving the discrete logarithm problem. Okay, so that means it is a hard problem. It's not as hard as we would like to have it. In the elliptic curve case, this is different. The best attack with elliptic curves is much, much weaker. Okay, that's if you use the best possible attack against elliptic curves, you only have to choose 256 bits. And it's still, you need 2 to the 128 steps to solve that. Okay, so the truth is really, yes, we can use elliptic curves to build another discrete logarithm problem that is hard, and it's even better. The discrete logarithm problem in elliptic curves is much, much harder than modulo p. Okay, so all of that looks good. The problem is, it's more difficult, it's more complex. That's why I warned you before. Be awake today. Okay. So from a level of 1 to 10, 1 is being completely asleep, 10 is, very much sunshine, right? Very much aware. It's now level 3, okay, so 4, okay, slowly wake up. So we start with something that seems very, very simple. Let's look at we look at polynomials, something we typically don't do. Polynomials that sounds like 10th or 11th grade gymnasium and not necessarily crypto. So we look at this baby here. And I think I've wrote that down before, right? What is this here? What kind of thoughts come into your mind when you see that equation here? Yeah? It's a circle, exactly. Okay, circle with radius r. Okay, and that's the first time you have to wake up, and it's very simple. You did that before in high school, in gymnasium. Why is that a circle? What makes this point here? If this is point P, why is this point on the circle? What is the condition here? Well, we look at the coordinates, right? We have an x-coordinate. We have a y-coordinate. If you take this number, on the x-axis, and this number on the y-axis, you plug it into the equation is fulfilled, right? That means this point belongs to this equation. This is simple, okay? But now, just to make that abundantly clear, to make that completely clear, is this point, V, is not on the curve. And why is that not on the curve? Because if you take this x-coordinate and this y-coordinate, if you plug it in the equation is not fulfilled. Everybody with me? So there are two types of points now in the world. Points on the circle here that fulfill the equation. All the other points are not part of that. Very simple, okay? This is analytische Geometrie here, okay? So, and of course and elliptic curves are similar type of polynomials, okay? So now we start playing with that. We vary it. Let's introduce coefficients. Okay. Anyone know what happens if we introduce A and B to the circle equation? What happens to the circle? Any ideas? What is the next shape, next form, geometrische Form? What happens if you start playing around with a circle? Yeah, you stauchen or strecken, right? So you get an ellipse. Okay, so we can play around with that, okay? what is very important, all of that is here, this is equations over. This is over the real numbers, obviously, right? This is the x and y axis are the real numbers, right? It's not modulo p, it's not the complex plane or whatever, this is the real number, okay? Kartesische Koordinaten over r, okay? So, for use in crypto, we need to consider polynomials over ZP. So it's so the polynomial we're considering, will be more or less the rest of this lecture. We are looking at polynomials, and we do all arithmetic modulo p with the, with integer numbers. So, and now I give you immediately the definition of elliptic curves. It looks really scary, right? You will think, oh, this is very confusing. What is Professor Parr doing? And then we will spend the next 60 minutes on explaining that. So, sometimes I like it more to develop all the material, but now we're doing kind of the opposite way. We're jumping in, I give you the definition, and then we talk about the definition and what this is all about. So definition, this is 9.11 in the textbook. If you don't want to copy that, you don't have to do that, but I write it down because we will need this definition. The elliptic curve over ZP, p greater than 3, is a set of all pairs x, y in the P, for which the following, and now comes the elliptic curve equation. This is an equation that will be very, very important. If you want to pass this course, you have to know the following equation, okay? Y square is equivalent to x cubed plus ax plus b. It's a similar equation to what we had before. I wanted to, not to make it look too arbitrarily. It's a polynomial equation, modulo p. But this is not all. Now it starts to become a little weird. It's not only the points here. You need something else together with an imaginary point at infinity. Punkt im Unendlichen. You might recall that you did that in analysis, in engineering, math, calculus, which is written as a O, Schreibschrift O, calligraphic O, okay? Schreibschrift O, erste Schuljahr, okay. Where you, and we also, this equation has to fulfill one additional condition, where, where a comma b are in ZP, and we need one additional condition, which is actually not that important for the rest of the course, but we need that for formal definition. For a cube is a hoch 3 plus 27b square are not equal to 0. Okay. Again, this is just, I copied that from the book, so this is just the definition. Okay. So now, the next remaining 60 minutes, we're going to talk about all the implications that follow from here. So maybe I start with the last one. This condition, normally we're not talking about this. This is an Ausschlusskriterium, so we want to certain curves have undesirable properties. They have properties that we cannot use in cryptography, and these are these curves, okay, for which this condition is not fulfilled. So this is one requirement, okay. Normally we don't, for this course we don't have to check for that, but this just to be complete. If this condition is not fulfilled, this is not an elliptic curve we want to use in cryptography, okay. So. The first thing we want to do, if you do that purely mathematical, it is really hard to understand and it looks very abstract and very arbitrary, sehr, sehr willkürlich. Okay? The nice thing is for this whole elliptic curve stuff, there's a very, very nice geometric interpretation to that, geometrische Interpretation, similar to the drawings we had here. And now we start with that. Now you have to slowly wake up. Okay? So let's look at an example for an elliptic curve. Y square is x cubed minus 3x plus 3. What we have to do in order to use that in cryptography, we have to do that modulo p. So we have to do modulo 17 arithmetic or something. Okay? The thing is, as soon as you start introducing this modulo operator, you can do that, and we're going to need that in cryptography, and your BlackBerry and your web browser, they do that with modulo p arithmetic. The thing, you cannot plot the stuff anymore. That means you cannot draw diagrams. The nice thing is you can take exactly the same equation and look of it first over R. Okay, so first we look at this over R, get a feeling, get an understanding how that works, and then later on we do exactly the same thing just with modulo operations. Okay, but with modulo operations, this graphical interpretation completely collapses. So you cannot look at that graphically and do modulo p arithmetic. So first we look at this over R. Okay. If you plot that, and nobody who didn't look into cryptography before knows what this shape is, it turns out that you get something like this here. Okay. Sometimes you give letters to these shapes. Let's call that uppercase E. That's the elliptic curve. It's a little bit like a whalefish, maybe like a whale. I don't know. So, okay. So one thing that we note is what happens with respect to the y-axis. It's symmetrical, achsensymmetrisch, right? It's symmetrical to the x-axis. Symmetry with respect to x-axis. And why is that? Well, this is very simple. We started this is a general equation, so we don't have to look at this example. Now we're interested in the solution, and the solutions means x and y points, right? So if you look at the solutions, if you want to compute, then you have to take the square root of this. Right, we take the square root on both sides. What happens, and you know that from calculus, from engineering math, you get the plus and minus solution for that, right? Meaning, if you have an x value, x equals to 1 here, right? Does it make sense? So x equals to x equals to 2, for instance. You plug in this example, x equals to 2, you compute the square root, x equals 2, maybe here. You get a y value, but the negative of this y value is also a point on the curve. Okay? This is how it works. It's always, it's not super important, but one explanation to get a little bit of feeling for this funny geometric shape here. Okay. Now we're through here. Okay, we don't have any blackboard left, so we switch. So where are we now? If you can, what you want to do when we started, we wanted to find. You see that here. We wanted to find a discrete logarithm problem, right? What do we need for a discrete logarithm problem? Is we need a group, right? For a DLP, we need a cyclic group for a group we need two things in particular. Okay, for cyclic group more specifically. For group we need I erstens, a set of elements, eine Menge, right? We need, what are the group elements? That's the question here. Any ideas? What are the group elements here? It's in the definition. What are the group elements for an elliptic curve? Very good. The points on the curve, and das ist ein Hammer. Okay. Before the group element, what were the group elements before? When we looked at just at ZP in Diffie-Hellman so far, what were the group elements? Again? Integers. So far, group elements were always plain old integers. 1, 2, 3, 4, 5, 6. My daughter Flor, our youngest kid, she's in 3rd grade. She knows these group elements, right? It's very, very simple, and it's almost too simple, right? Because we think, a group is, we just do integer arithmetic, no big deal, right? What we're getting now is suddenly we start to build a group where the group elements are something much more abstract, namely these things here. These are the group elements. Okay, so that's the first thing. They're much more abstract, and maybe you don't really know what I'm talking about. You just think, this is not that abstract, it's point on the curve. But now comes the weird thing. What is the second thing, the main thing that defines the group? It's not the ensemble, it's not the set, it's not die Menge. What do we have to do with the group now? What is the second thing that we need? We have to compute on the curve, right? We have to compute in the set. A group operation that fulfills the group laws, diese Gruppengesetze. Okay, and we're going to talk about this. So now I'm very sorry, but you have to wake up at this point here. Okay, from the next 20, 30 minutes, they will be crucial for this morning. Okay, so when we talk about the group operation, so let's step back. So what do we want to do? Well, looking at the points, again, maybe that didn't really seem all that abstract because we did that in 10th grade or 11th grade when we did analytische Geometrie, right? But now we're going to do something you've never done in your life. You're going to, buckle up, hold on. We need to compute with these points. We have to add those points, and there's no natural way of doing that. This is something very artificial. This is the complicated stuff of elliptic curves that comes now. Okay, and this is the second part of the lecture. we're done with the easy part, introduction, right? Now we look at the group operation. That's the hard part. So, okay, so group operation. What you want to do now comes this super important drawing for the rest of your life. Well, it's the rest of the lecture. So you need about 1/3 of this is my drawing, right? You need 15 Kästchen, okay? So if you're at the end of the page, flip over. Again, we draw one of these beautiful elliptic curves here. So, what I would like to ask you, meine Bitte an Sie, stop copying from now on and copy in 10 minutes or so. Because it will be very subtle whether you put the points here or here, and in one point your drawing doesn't work out. So just wait, don't copy for a little while, and I tell you in 10 minutes I say, now it's time to copy. Okay. So the goal is now, again, the set of elements are the points. Now we want to find ways of doing arithmetic within computing with the points. So, and what we try to do is, let's assume we have a point P here, and I have to be careful here what I'm doing, okay? And we have a point Q at this point, at this location. And now the question is, how do we do that? How do you add 2 points? Okay. Maybe it should shock you a little bit. Okay, I'll shock you. Okay. So I can. The end of the story is, we will be in 10 or 15 minutes or so. Is boop, 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 boop. 1 second. That's the end of this discussion that's going to happen now is here. Is this here? You see this box there? Really scary, right? Okay, so that's the bad part of it. And that's if you want to be a bad professor, you write these formulas on at this moment. I try to be a good professor, and this is what we're going to do. There's this very beautiful geometric interpretation for that. Okay, again, and this is of course considering the formula. This formula, not with modulo p, but over R. Of the reellen Zahlen, of the real numbers. And you get this plot. And over R, don't look at that. Look at me. Okay, and here. Okay, here's the geometric interpretation. Everybody awake? Very good. So, here's the geometrische Interpretation. Okay, the geometric way of doing that with ruler, right, with lineal and paper. You want to add the points. Here's the construction method. You put a line. That's not a lie. I told you, don't copy, right? So I think that is funny. So this is better. You know what I mean, right? Okay, so you connect the 2 points. Okay. So you connect, it's terrible. I'm bad at drawing. I'm really bad, okay. This is better, okay. Sorry, okay. So you connect the points, you get a third point of intersection, dritter Schnittpunkt, okay? This third point of intersection is being mirrored. You end up here, and this point is by definition, there's no natural something to it, it's just by definition, this is B plus Q. Okay, so two things what you have to do. If given 2 points, you want to add them up. You know, die Gruppenoperation is Addition. The group operation is addition. You compute the sekante, so you compute that here, right? The line through the 2 points. You get a third point of intersection, and then you mirror this point. And this resulting point R is by definition is a group operation. So this is point addition, and now we have to switch the color, because to make things worse, we have to distinguish two different cases. So this is point. This is called point addition. P plus Q is equal to R. And there's one situation where this doesn't work. Again, now I'm telling you for the third time, what do you want to do? If you want to add 2 points, well, draw a line through the 2 points. Okay? But what can happen is that you want to do point doubling, meaning the point you want to add, you don't want to add P plus Q, but you want to compute P plus P. Okay, the point to itself. It's like 3 plus 3, right? With modulo P, we can do that. This construction method doesn't work anymore. I mean, how do you draw a line through 1 point? And does anyone have an idea what we can do instead? Maybe let's go back to analysis, to calculus. What happens if the point Q walks along these lines here? Okay, now try to graphisch, try to imagine what happens to this sekante here. If we go down here, this starts shifting, right? Everybody with me? And what happens towards the end? If Q is here, it's still clear what we do, right? We do this and we get up there somewhere, we get the third point of intersection. But what happens if Q gets closer and closer? And what happens if P actually becomes Q becomes P? What happens here with this sekante? Tangent, right? It becomes a tangent, becomes this 1 point. Okay, so, and maybe let's do that here. Let's give another name. If this is the point V here, okay, let's change the names here. What happens here? So you compute the tangent, which is maybe. And from there on, you do the same thing. You get not a third point of intersection, you get a second point of intersection. You mirror that, and this point becomes 2V. And I meant to use a different color for this. Okay. Again, this is kind of the beautiful part of elliptic curves. This is funny geometric construction to it. So now the question is, how does our BlackBerry does that? Because you don't want to start drawing funny pictures on a BlackBerry, right? You don't want to do that. So that means a BlackBerry or any kind of embedded device or any kind of laptop or PC or server or whatever, special hardware, has to do that with only doing computation, not using, graph paper and ruler and stuff. So what we want to have for this, we want to do the same construction here, but doing with numbers without, drawing stuff. Okay, so analytical expression for the group operation. Analytische Ausdrucke sind formulas, right? Analytical expressions is really fancy way of saying we would like to see formulas here. Okay, and you do see the formula. The formula is a box up there, and I want to give you, in order to derive that very nicely, we will need most of the lecture today. So I'm going to do that quick and dirty to give you a little bit an idea, and probably in the exercises, in the Übungen, Markus is probably doing that with you more slowly. But I want to give you a little bit the idea, how do we end up with these formulas over there? Idea. Given is obviously the elliptic curve x cubed plus ax plus b we have one point given. I'll write that here. So we have a point P given, we have a point Q given. This is the starting point, right? You have the curve, you have 2 points. Now, how do we do this funny geometric construction here? Remember, the first thing we did, and this is actually for deriving the formulas, the main thing, we have to connect those points, right? We have to find the line to the point. So what we are looking at is the point. So the first thing that you do is G, the Gerade, the line G or L in English, probably I call that G here, it's more the German. I call that L, okay, for line. What the heck? So this is what, when 9th grade, the teacher calls it G in Germany, right? For Gerade, we call that L for line. So what is the equation for a line, for a Gerade? You vaguely remember, right? It's something with x, right? And 2 coefficients, right? What do we need here? Anyone know? Exactly. So we call that S. So does anyone know whether this is called S in English? Or in German too. What is this S parameter? Same letter. That's the Maß für die lauter Steigung, right? The slope. And we call it S, right? In English, slope, in German, Steigung. It's an S. Is there an S in the formula? Yeah, do you see the S there in the box? That's the S, okay? You've seen that in your life before here. You know what I'm talking about? y2 minus y1, blah, blah, blah. This is the slope. This is in 9th grade. Everything is fine, okay? It's not that scary, okay? Plus a... which we call M, okay, which is less spectacular, okay? So the first thing, find that we know how to do that. This is 9th grade. 2 points, define a line, okay? Given x1, y1, x2, y2, you can define this equation, okay? We're not doing that here. Again, this is just the idea how you do that, okay? So what do we do then? Again, this is now 10th grade high school. You have this equation of the funny curve. You have the line. You want to have the points of intersection. How do we find that? Schnittpunkte zweier Kurven. How do we do that? What is the magic word? You have two geometric things. How do we find the Schnittpunkte, the points of intersections? Gleichsetzen, okay? You equate them. Very, very good. Gleichsetzen, that's what I mean with that, okay? So how do we do that? You know, this is y, and this is y squared, so we square that. See, so sx plus m square, this is L square, must be equal to x cubed plus ax plus b. Okay. This is a Bestimmungsgleichung. Okay, so this is a determining equation. What are the unknowns here? You know, A, B, S, and M are parameters, are coefficients. What are the unknowns here? What's the independent variable? It's x here. Okay. What degree does this equation have here? 3, right? It's x to the 3, so it's the equation of degree 3. How many solutions do we have here in general? Fundamentalsatz der Algebra, how many? 3 solutions, right? So in general, finding solution of a cubic equation can be very, very hard. But why is that not super hard here? What kind of, do we know any of the solutions here already? Yeah, of course. x1 and x2, we have 2 of the solutions, right? So we have 2 of the 3 solutions, so you can somehow insert them and abspalten and ausdividieren, you know, all the stuff you do in 9th grade or 10th grade. And however, if you solve that, three solutions. x1, which we know, x2, which we also know, and now is the interesting thing, and x3. So, okay. No. Sorry. Meaning x1, or you call kind of xp if you wish, but you know normally we call it x1 here. x2 we have as well, and the only thing missing is x3, which we get out of this cubic equation here. Okay, it pops out. If you do that, more slowly, and actually you do all the step, again, this takes 30 minutes or so. If you do that really slowly, maybe more, and you will probably do that in the exercises, you end up with these formulas here. Okay, this is a group equation. This is what happens on your BlackBerry. Okay, they do this addition, these computations. If you want to add p plus q, what you have to do, you start with s, with the slope. Means you compute this quotient here, this fraction here, y2 minus y1 divided by x2 minus x1 modulo p. You get in value s. You plug and modulo p s is some value, and in practice it's a long number, it's a 200-bit number. You square it, you subtract x1, you subtract x2, you get x3. Okay? Why is that? Follows from here. Okay? I don't want to do that here. I don't want to spend all this time on that. Okay? And then in order to get the y coordinate, that means in order to get where are we here? Y is 3. You do the last part of this formula, you compute this expression here. Okay? So this is just plug and play. Okay? If you just want to do these arithmetic steps. So what we need at this point here is elliptic curve point addition and doubling formula. This is a very fancy word of building the plural of formula, right? Very often people say formulas in English, but this is really the Latin plural if you want to use good English. Page 244 in our textbook, okay? So let's step back. It's very good. No, you still have to stay awake. I'm sorry. So we continue. Now it's another 15 minutes where I'm going to do weird stuff. Yeah. Good question. Fragt, dass hier der Bruch nicht ganzzahlig ist. And this is, we don't have to do a plain old division here. Wir machen keine normale Division, sondern, gute Frage. Was? Genau, we compute the inverse, right? Very good question, very good question. So his question is, if you do an inversion here, you normally would get a rational number, ein Bruch, right? And this is why we don't do this division here. Which algorithm do you use at this point here? Extended Euclidean algorithm for inverse. Okay, very good. So, any more questions at this point? Otherwise, I continue with my weird elliptic curve stuff. Okay, so I continue with the weird elliptic curve. So, what can we do now? I showed you ways of adding 2 points. Okay. What we really want to do is, at this point, they said, well, for a group, we need a set of elements in a group operation. And now we do have the group operation here, which is with the funny formula there. And this is unfortunately addition that fulfills the group laws. What are group laws? This is stuff we did when we talked about AES in November, which is on page 92. Let's jump back on page. I'm close here. Okay. So we have to fulfill all these laws here that we see here at this point. Okay. A group is a set of elements G together with an operation, which we call donut here, right? Circle. And we call that plus here, right? The group operation, by the way, is called plus. It's P plus Q. We could call it donut or multiply, but we call that plus. First of all, the group operation is closed, abgeschlossen. That means if you compute A plus B, the result must be on the curve. Is this given here with this construction? What do you think? Absolutely, right? We always talk about points of intersection. It cannot be that we end up with a point which is somewhere else on the plane in der Ebene. Okay, so closed is kind of built in our construction method. Group operation is associative. What is? We don't see that, but it's associative. Believe me. Okay. So now comes the hard part. So group laws 3 and 4, they are kind of painful because we look for an identity element, which we called 1 here, and actually we call that 0, right? Because it's addition, and we need an element that fulfills this property here. So what we need is question, what is the neutral element? That means what we need, neutral element in an additive group means P plus we need this here. We need a point. Normally we would think we need a point here so that P plus this specific point is always P, and this must stay constant. So, we call it 0, let's say. Okay? It's null element, right, in additive group. Okay? And now, if you start looking which point can we choose so that this is given, if we choose this point and we do this geometric construction and we do this mirroring and stuff, and it turns out it doesn't work. There's no, which is frustrating. So there's no point on this curve that can serve as a neutral element, as a null element, as a 0 element. Okay? So what we do here is a really, really dirty trick. We artificially define a point. Okay? Which is really the part that is not very nice to teach because it seems somewhat willkürlich, arbitrary. Okay. So we define, and please underline define. Okay, das ist eine Definition. Das ist, I wouldn't say arbitrarily, it's not willkürlich, but it's a definition. It's not something that comes naturally, necessarily. We define a, in quotation marks, point at infinity. Okay. For which we use this calligraphic O, Schreibschrift O. This is what the literature does normally. Okay. If we do that, the following property 3 of, what is this, of definition 4.3.1 is now P plus 0 is P for all P element in E in the elliptic curve. Okay, and what is this point of infinity? What more or less works geometrically, again we come back here. Well, this point is called point of infinity because you can imagine it as a point either in plus or minus infinity along the y-axis. Okay, if you imagine this, the geometric construction more or less work. I do a little bit of this kind of a Gedankenexperiment here. So if you want to add P to itself with the point, this is up high in the sky, very, very high up, okay? And now you have to connect this point with the point up in the sky. What happens, how does the line goes? Becomes a straight line going up here, Okay, can you imagine that? Up in infinity, if you're high enough up, if it's a little bit in the right and it's not really high up, you get maybe something like this. But if you go to infinity, this secante becomes this vertical line here, okay? So now we look for the third point of intersection, but where is the third point of intersection then? If we have a straight line, we get the third point of intersection here, right? So that would be equivalent to this point here, right? And what was the next thing that we did then? We mirrored again, right? Gespiegelt. Oops, we're back at P. Okay? And this is exactly what we want here, right? P plus point of infinity is P. Again, so this more or less works, right? It's a little bit hand-waving. It's not very sharp, but it helps us to understand. Okay? And now, really, I think actually the more interesting thing happens here. Once you have your point of infinity, you have to fulfill property 4 of the group definition, namely, this says, you start with this. Now we're looking for any point, for all points on the elliptic curve. We also need another point, which is the inverse, such that P plus its inverse is equal to this neutral element. Okay? And this point is called minus P, of course, in additive notation. It's really bad. It's kind of unfortunate because here we have for this sign here, for the donut, okay? For the donut, we use this, we thought this is more like a multiplication. We called that to the minus 1 because it's multiplicative. But here if you have additive, you use the minus 1. You use the minus operator, okay? So, where is P? And now P is minus P. Minus P is not some kind of weird point of infinity. This is a very down-to-earth, handfester Punkt, right? This is a real point on the curve with real coordinates. And this is where this whole geometric interpretation kind is not all that nice anymore. It turns out that, again, you connect the P with the point of infinity. You get a third point of intersection, and this point of intersection is actually here, which is minus P. Okay? That's the gespiegelte Punkt, right? You mirror the point, and you immediately have the inverse of the point. And now this kind of weird things are happening here. From this, it follows that minus P of P equals x comma y is by definition minus P and what is the y coordinate here from the drawing? What do I have to write down here at this point? Minus y. And now comes something which is really weird. What I'm going to tell you now is so one thing which is good, finding the inverse of the point, finding an inverse in the group is really easy. And people who stay with me, actually, who take in the 5th semester, I have kind of, as a course by me, Implementierung kryptographischer Verfahren, implementation of cryptography, which you can vaguely view as a continuation of this lecture. And there's actually special methods of doing really fast computation with elliptic curves, so we need this property. We need the property, given point x and y, it's really easy to find the inverse of the point, which is not the case here finding the inverse modulo p, we have to do Euclidean algorithm, which is very painful. It's a lot of work. Here it's very easy. Okay, now pay attention for 60 seconds. Now comes something just to show you the weirdness of the stuff that we're doing. Look at this line and the two minus symbols, right? Minus p, minus y. It turns out these two minuses are something completely, entirely different. Okay? This minus is exactly the minus, essentially the minus you know since Grundschule, right? Since elementary school. This is the minus of the y-coordinate. Okay? It's really minus modulo p. But you know that since the first lecture here, since October, right? This minus is something completely different, right? This minus is this weird thing coming from the group operation here, okay? And it's very unfortunate that we both use the minus symbol for that here, okay? This is all I want to say. Once you start doing the homework, at some point you will say, oh yeah, I guess yeah, he talked about this minus, right? It's something completely different, okay, just to warn you. Gut. What I want to tell you now is maybe let's look at an example. Okay. And I just walk you through this example here on the to put a little bit life in all the stuff we did so far. Okay. So we have this toy example. So we're not taking a curve with 200-bit numbers, but we take a curve with a 5-bit number, right, with modulus 17. So this is the curve we're looking at. And what we just do in this example to one group operation, right? We do p plus p here, okay? P has the coordinate 5 plus 1 plus 5 plus 1. The first thing, which is people who were really heavily asleep today, okay? What they are doing here is they look at this here. And what do really stupid people say at this point? They say this is 10-2, right? Everybody with me? This is very, very, very wrong. This is not vector addition, okay? This is why I said it's good, it's good that you spend the 90 minutes with me here because you're not making the stupid mistake here. So there's something really weird happening, namely what is happening here, you need this group formulas here. The first thing that we do, you have to compute S. S looks very different here. And why is that? Because this nice thing with, taking the slope here is only if P and Q are not equal. If P and Q are equal, you have to use this type of the formula. This was the Tangentenfall, right? The Tangenten. And actually, if you're really good, this has, what you see here, this has something to do with the derivative, with the Ableitung. Okay? Not going into that here. Implizite Ableitung ist das. Okay, so, however, you compute S, with, you plug in numbers for x1 and for a and for y1, blah, 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 blah. S, the slope, die Steigung of this tangent is 13. And now you plug the other numbers in. You compute x3 by using this part of the formula. x3 is the value 6. Then you compute the value for y3. Again, it's just use the formula. Y value is 3. And now the result is, this is kind of an important thing here to imagine that adding 2 points, you end up with another point, 6.3. What is a good trick if you do homework or if you take the exam here in September, it's pretty easy to make some mistake here. You know, if you do this computation, what's a good check here is the result must be a point on the curve. How do we know that it's a point on the curve? How can we check that? Put it in the equation, right? And that's what we did here. You know, we go back to this, that's a group equation. And here you have 6 is the x-coordinate, so we plug in 6 here. And here we plug in 6. And 3 is the y-coordinate. We plug in 3 here. And we check whether it works out here. And of course, they didn't make a mistake in the book, so it works out here. Okay? So, and this is what you have to do from now on all the time. Every time we give you homework assignments with elliptic curves, you're going to hate that. Okay? You always have to do these formulas. Was? Das ist Seite 245, 245. Okay? I don't want to copy that. I think it's good to talk about. It's enough to talk about. So now comes a final theorem, and we will have another week on elliptic curves next Wednesday morning. Okay. There comes one final theorem, and that's the end of today. Then is the points on an elliptic curve including this point of infinity O, because there's one little detail we haven't talked about. Everything we talked about so far is we want to build a group, we want to build a group, we want to build a group and fulfill the group properties. We don't want to have any group. What kind of group do we need for a discrete logarithm problem? What kind of adjective am I looking for? Welches Wie-Wort, okay? We don't need a plain old group, but a cyclic group, right? And proving this would be, I don't know, we need to study 1 year of number theory. So it's just a theorem here, right? Namely, the points on the elliptic curve, including O, have cyclic subgroups. Whatever subgroups is something we haven't introduced here either. Under certain conditions, also in manchen Fällen, under certain conditions, all points on an elliptic curve form a cyclic group. And there is actually an example here. And I'm going to repeat that next week, but I'm afraid you need that for the homework assignment. So you have the same elliptic curve here that we had before, okay? And now, what I'm doing here, this is on the next page in the book, okay? It's on page 246. (246). What you see here, you see a point P has this coordinate, 5.1. What you see here is a long list of points, right? 2 points, 3 points, 4 points, blah, 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 blah. 2P, 3P, 4P, up to 19P. 19P is equal to the point of infinity here, right? Okay. So we have 19 elements in this group. It turns out this is a cyclic group, with all the weird things that happen with cyclic group. What is the big thing? When do we have a cyclic group? What is this one main condition that we have to fulfill? There's only one condition. We need a special type of element, namely a generator or primitive element, okay? And for instance, here in this example, 2 is a primitive element, right? Here we compute 2p, 3p, 4p, 5p. We do this whole thing that we did before, right? Before it was multiplication. We had A, a square, a cube, a to the fourth, a to the fifth, a to the sixth. Remember all the stupid examples I did here for you on the blackboard? We do the same here in the book, okay? So you just keep adding p to itself until, when we did modulo p, we were looking for until a to the 10th was equal to 1. Remember that? Now we have to check for until 18, 17p, 18p, 19p. We have to check whether this is a point of infinity. Okay? That's it for today. Enjoy the homework.